Today my topic is under network topology, incidence matrix, basic tie-set matrix and basic cut-set matrix. So first about incidence matrix. So what is meant by incidence matrix? An incidence matrix represents the graph of a given electric circuit or network. So incidence matrix represents the graph of a given electric circuit, and so it is possible to draw the graph of the same electric circuit from the incidence matrix. That means if incidence matrix is given, we can draw the graph. Okay, if incidence matrix is given, we can draw the graph of the electric circuit. And here the connecting of branches to a node is called as incidence. The connecting of branches to a node is called as incidence. Now, incidence matrix is a representation of concepts of Kirchhoff's voltage law and Kirchhoff's current law applied to a network. Incidence matrix is represented with the letter A, and this incidence matrix is also called node to branch incidence matrix, node to branch incidence matrix, or node incidence matrix. Node incidence matrix. Now, clearly we see what is the what is this incidence matrix and how it is formed. If there are n number of nodes, and b number of branches present in a directed graph, okay, then if there are n number of nodes and b number of branches in a given directed graph, then the incidence matrix will have n number of rows and b number of columns. N rows and b columns. Here that means rows and columns corresponding to the nodes and branches. Okay, that means what? Rows and columns of the incidence matrix corresponding to the number of nodes and branches of the directed graph. Hence, the order of the incidence matrix will be n by b. The order of the incidence matrix will be n by b. Okay. Now, so that is basically the order of the incidence matrix. Okay. The order of the incidence matrix is given by n by b, where n with respect to the rows, b with respect to the columns. So rows is nothing but number of nodes. Okay, b is with respect to the number of branches present in the given graph. Now, what are the elements? What are the elements of the incidence matrix? Okay, now, so see that the elements of the incidence matrix will be having one of these three values: +1, -1 and 0. Okay, the elements are given by +1, -1 and 0. These are the only elements present in the incidence matrix. See that if a particular branch current is entering towards a selected node, then the value of the element will be +1. If we take a particular branch current in a given graph, directed graph, if it is entering towards a selected node, particular node, then the value of that element will be +1. Then, if a particular branch current is leaving from a selected node, then the value of the element will be -1. If it is leaving, okay, if a particular branch current is leaving from a particular selected node, okay, then the value of the element will be -1. Okay, then if the branch current is neither entering at a selected node nor leaving from a selected node, then the value of the element will be 0. That means it is no way connected. If a particular branch is no way connected to a selected node, neither entering nor leaving from a selected node, then the value of the element will be 0. So that is how the incidence matrix will be formed. Okay. So now we look at a problem. We take a directed graph example. We take a graph and we write down the incidence matrix for that considered graph. See that. So to write down the incidence matrix, these are the points we need to keep in mind. Okay, basically the order of the matrix is n by b. N represents the number of nodes, b represents the number of branches, and the elements are plus 1, minus 1. Okay, only 3 values, plus 1, minus 1, 0. Okay, then when it is 0, when it is plus 1, when it is minus 1, these are the 3 points. If you take a branch, okay, with respect to a selected node, if it is entering towards that, then its value will be plus 1. If it is leaving, minus 1. It is neither entering nor leaving from that selected node, then its value will be 0. So look at this example. This is a considered following directed graph. So you can see the circuit here. So electrical circuit. Okay. So then its equivalent graph is also given. Okay. That is the next picture, second picture from the left side. So first one. Okay. So this is a, let us say, given electrical circuit. So there are 2 voltage sources and the resistors are given here. Okay, like this, R1, R2, R3, R4. So there are 4 resistors present in the electrical circuit. Okay. Now, so draw its equivalent network graph. Okay, so already we know from the previous lecture how to draw a graph. Okay, for a given electrical circuit or network. So we know that in a graph, number of nodes are same as the given electrical circuit, and branches equal to or less than, okay, of given circuit. So to draw the graph, one more thing. Passive elements, voltage sources are replaced with short circuit and current source replaced with open circuit. So come to the circuit. Here the number of nodes are already marked. Okay, so we start from the first source V1. So the first point, common point where more than 2 elements are connected, so it becomes node 1. So node 1, this is. Then if you look at the second point, this is also a node because more than 2 elements. So this is, let us say, node 2. Next point, okay, you can see there are also more than 2 elements connected. So this is also node, say node 3. And come down, the point, this is not a node because not more than 2 elements connected. So next point, this is a node, let us say node 4. Then next one is not a node. So there are 4 number of nodes. So that's why it is mentioned here. Number of nodes are 4. And here branches, you can see elements are sources present. 2 voltage sources and 4 resistors. So that's why it is mentioned branches 6. Now, to draw its equivalent graph, come to the next picture that shows its equivalent graph. Okay. So here mark the nodes, so which are same as the circuit. Number of nodes, so node 1, node 2, node 1, node 2, node 3, node 4. Okay. Now, so first from node 1. From node 1, what are the elements present? From node 1 to node 2, you can clearly see. So, okay, first with respect to node 1, okay, So draw the branches. So from node 1, voltage source is there which is connected to node 4. So voltage source replaced with a short circuit, we know. Okay. And all passive elements also replaced with a short circuit. So V1 is replaced with a branch. So here one branch, okay, between node 1 and 4. Okay, we mark the branches. We mark the branches later. Branches we know that we are representing with small alphabetical letters. So we mark that later. Just I'm showing the branches first. So between node 1 and 4, one branch. Next from node 1 to node 2, there is a element R1. So between nodes 1 and 2, there is a second next branch. Okay, one more branch you can draw. Then from node 1 to node 3, there is R4, element R4. So draw a branch between nodes 1 and 3. So from node 1, all the elements are represented. Next, come to the node 2. Node 2 to other remaining nodes. So between node 2 and node 1 already we have drawn. Okay, then from node 2 to node 4, there is one more. There is one path, one resistor is there. So draw that. Okay, a branch. Then node 2 to node 3, element R2 is there. So draw the connection, a branch between nodes 2 and 3. So from node 2 also all elements are represented. Okay, now from node 3 already it is drawn between node 3 and 1 already drawn. Okay, node 3 and node 2 also already drawn. Now node 3 to node 4, there is a source V2, voltage source V2. So node 3 to node 4, draw that with a short circuit. So now all the elements are represented, okay, in its equivalent graph. Okay, now see that branches. So randomly we can take which branch is A, B, branch is C, branch D, branch E, branch F. So we can take as our choice. So I have taken, this is branch A, whose direction also our choice. So it is, I have taken like this. Node branch A is the branch current. The current in branch A is flowing from node 1 to node 2. So this is A. Then I have taken, this is branch B, whose current direction is I have shown like this, flowing from node 3 to node 2. Then next one, this is branch C, along with its direction I have taken like that. Next branch D with its direction, branch E. Then the top one I have taken branch F. So that is how all the branch current directions also indicated. After drawing the branches, all the branches take the represent the branch current directions also. Now now write down the matrix. Finally, what we want to write down the incidence matrix. Okay. So we know that the order of the incidence matrix is given by n by b. Okay, means n represents rows, b represents columns, where n is nothing but number of nodes present in the graph. So how many nodes? 4. Okay, so 4 rows. So n1, that's why it is shown n1, n2, n3, n4. 4 number of rows. And the columns in b number of columns represents the b number of branches. Okay, how many branches we have? A, B, C, D, E, F, 6. So that's why it is the number of columns in the matrix is shown 6. Okay, which are indicated with the branches. Okay, A, B, C, D, E, F. Okay, now, so this is a 4 by 6 matrix. 4 by 6 matrix. Okay, Now, so the values are the elements, okay, in the incidence matrix. So we know that how to write down. In the previous slide, you have seen if a particular branch current is entering towards a selected node, then its value will be +1. If it is leaving, minus. If it is neither leaving nor entering, 0. So consider first branch current A. For particular branch current A, if you see in the graph, it is leaving from node 1. Okay, it is leaving from node 1 depending upon its direction. If it is leaving from node 1. So under branch A, you have to write down at node at node 1 -1, and it is entering towards node 2. That's why at node 2 you have to write down +1. It is connected between nodes 1 and 2. Okay, it is leaving from node 1, so -1. It is entering towards node 2. That's why +1. Next, remaining, it is not related to node 3 and node 4. Okay, neither entering nor leaving. Okay, with respect to those nodes. That's why the remaining two nodes, with respect to those two nodes, its value will be zeros. Next, if you consider the branch current B, branch current, if it is connected between nodes 2 and 3, it is leaving from node 3. So at node 3, its value will be -1, and it is entering towards node 2. That's why at node 2, its value will be +1. Then the remaining two nodes, it is not related, neither entering nor leaving. That means, so remaining two values will be zeros. Next, if you consider branch current C, it is connected between node 1 and node 4. Node 1 and node 4. It is entering towards node 1, so that's why at node 1 it is +1. It is leaving from node 4, there its value will be -1. Okay, so that's why it is shown written, and the remaining two nodes, it is not related, so remaining two zeros. Next, branch current D. Branch current D is connected between nodes 2 and 4. It is leaving from node 2, that's why -1 there, and towards node 4, it is a +1 there. Remaining two values will be zeros. Branch current E. Branch current E is connected between nodes 3 and 4, entering towards node 3, so +1 there, and leaving from node 4, -1 at node 4. Remaining two values will be zeros. Next, branch current F. It is connected between nodes 1 and 3. Okay, nodes 1 and 3. It is leaving from node 1, so at node 1, its value will be -1, and entering towards node 3, so at node 3, its value will be +1. Remaining two values will be 0. So that is how the incidence matrix is written for this given example graph. Okay, example electrical circuit. So basically we have the circuit, so we have drawn its equivalent graph, then we have written the incidence matrix A, which is denoted with letter A. Okay, so that is how incidence matrix is written. So vice versa also possible. As I mentioned in the first slide, we can draw the graph. We can also draw the graph from a given incidence matrix. Suppose this incidence matrix is given, okay, in the question, if they ask to draw the related its corresponding graph, you can draw, yes or no, because we know that number of rows, columns gives the number of nodes and branches of the graph. So accordingly, we take the number of nodes, okay, and we can, by looking at the values, which branch is connected to related to the which, okay, node. Based on that, we can draw the branches along with the directions. So that is how we can draw the graph from a given incidence matrix. So that is about the incidence matrix. Then basic tie set matrix. So basic tie set matrix. Okay, what is meant by this matrix? Okay, for a given tree. Okay, a tree is there. Okay, for a given tree, if we add a link, addition of each link between any two nodes, it forms a loop. It forms a loop. Loop means a closed path. So, which is called fundamental loop or tie set. Okay, for a given tree. Okay, so if a tree is given, if a tree is there, okay, then or we have to consider the tree. So basically, to write down the tie set matrix, we have to take the tree. That is how. Okay, for a given tree, if we add a link means what? Branch of the core tree. Okay, we will do a problem, then you will understand. Okay, basically the definition, what is meant by tie set means, for a given tree, if we add a link between any two nodes, it will form a loop called fundamental loop or tie set. Fundamental loop or tie set. Now, in a loop, there exists a closed path. So there is a circulating current which is called link current. Okay. In a loop, there is a closed path, so a circulating current which is called link current. Now consider the tree here they have shown. So from the previous lecture you know that, right? The solid lines represents the tree and the dotted lines represents the core tree. Okay. So here the tree is with the branches D, E, F. Okay. So tree means what? Basically you need to remember that one also. Okay. Tree means it is a subgraph. The number of nodes are same as the original graph without closed path. Okay. Without closed path. So here the tree is with the branches D, E, F. Okay. Now, so see that here to form the tie set or to form the loops, fundamental loops. Okay. For this example, you can see, okay, tree, we can get three loops, three tie sets. See, it is written loop 1. Okay, tie set 1. Loop 2. Loop 3. Okay. Tie set 1, tie set 2, tie set 3. Okay. Now, so tie set means we know that for a given tree, if we add a link, one link, okay, only one link, it is it will be a loop. There will be a loop. Okay. So now, with the tree DEF branches, DEF, we added only one link, that is A. So what it is formed? There is a closed path. Yes or no? There is a loop. So that's why it is called, okay, loop, and which is named as loop 1 or tie set 1. Next, second one, with the same tree DEF branches and if link B is taken, then the closed path you can see, okay, which is named as loop 2. Then the next one, with the same tree with the branches D, E, F, link is C, then there is a loop which is named as loop 3. Okay. Now, how to write down so that is basically what is meant by tie set. Okay. Now, how to get the tie set matrix or basic tie set matrix? Kirchhoff's voltage law. Kirchhoff's voltage law can be applied to the F loops or loops, tie set, okay, tie sets. To get the set of linearly independent equations, okay, Kirchhoff's voltage law, they are telling that KVL can be applied. Okay, to get the KVL can be applied to this fundamental loops, tie sets to get the independent equations. Okay, consider the figure above. Here you can see. Okay, there are three tie sets or fundamental loops, F loops. So, how many link currents? Three link currents. Three link currents. Okay, three loops, so three link currents. Now, to write down the KVL, we have to note down the voltages, right? We have to write down in terms of voltages. So, consider branch voltages. How many branches we have? We have A, B, C, D, E, F. So, accordingly, take the branch voltages VA, VB, VC, and so on, VF. Okay. So, VA, VB, and so on, VF are the branch voltages. Then the KVL equations. Okay. For the fundamental loops can be written as, let's see the next slide. Okay, to write down the tie set matrix, finally KVL is applied in each loop. Okay, using the knowledge of KVL equation, we know the sign convention for KVL equation. Okay, in terms of branch voltages here. Okay, what are those branch voltages? VA, VB, and so on, depending upon the number of branches present in the graph, in the loop. Okay, we form the equations, we write the equations, and we put that in a matrix form finally. Okay, now, so finally writing tie set matrix. Consider the graph here, you can see. So on the left side, so the graph is taken, clearly taken with a tree. The solid lines shows the tree taken. Okay, so remaining are the links. So here clearly we know already. So there are three links present. So three loops, three fundamental loops or three tie sets we can form. So here, to write down the tie set matrix, first thing we need to know is this matrix is denoted with the letter, represented with the letter B, capital B, and the order of the tie set matrix is given by L by B. L by B, where L represents the number of loops. Where L represents the number of loops. Okay. And B represents, as we already know, branches. So the order of the tie set matrix is given by number of loops. Okay. Number of loops and number of branches. So basically we need to know how many loops are present for a given tree, then automatically the matrix order also known. So here how many loops are present? 3 loops are present. That's why the order of this tie set matrix B is given by 3 by 6. That means 3 rows and 6 columns. Okay, now write down the equations. Okay, so we have to write down the using KVL, get the equations, write the equation in each loop. Okay, so then put that in a matrix form. So for the first loop, KVL is applied. Okay, so I have a assumed path. Okay, so we have to assume a loop current path. Now you can write down the KVL equations. Okay, so in the first loop I have taken the loop current direction like this. Now the KVL equation, okay, for the loop 1, first loop 1. For the first loop 1, start from here. We know that KVL equation, if the assumed current, direction is same as the branch voltage direction, then that is taken with negative sign. So what is the branch voltage? Vf, first branch. So minus Vf, because branch current direction also same as the assumed current. So minus Vf. Next, follow the direction. Okay, what is the next branch voltage? E. Okay, along a loop, VE. So its direction is opposite. So plus VE. Next, what is along the loop? What is the next branch? C. So the next voltage is VC, which is same as the whose direction same as the assumed current. So minus VC. That's all. The loop is completed. So the loop is completed. So the equal to 0. Now see that. Now putting that in a first in the matrix. So first this is a first equation. So loop 1. For loop 1, what are the elements? So minus Vf plus VE minus VC. So coefficients. Okay. So here you can see first branch is VC, next VE, VF. So VC minus 1. Okay. So if you multiply this with minus, what is this equation? VF minus VE plus VC is equal to 0. Now put the coefficients now here simply. VC is plus 1. Next element is in order E minus VE, so minus 1 plus VF, so plus 1. That's all. Next, for loop 2, write down the KVL equation. KVL equation, what is a KVL equation? So for loop 2, so assume a current direction. Okay. Assume a direction in the loop. Okay. Loop current direction. Then write down the KVL equation. What we will get? First element is VA. So minus VA. So yes or no? VA minus VD minus VC equal to 0. Okay. In that loop, those are the 3 branches, 3 branch voltages. Now multiply all are minus. So minus with multiply with minus. So all values will be plus 1. So put that in my matrix. Second equation for loop 2, VA plus 1, VB not there, so 0, VC plus VC, so plus 1, VD plus 1. So next VE, VF not there, so remaining 2 are zeros. Next, loop 3. Loop 3, same, assume a loop current, link current direction. Like this I have taken. So write down the KVL equation. Plus VB, yes or no? VB current is opposite to the assumed current. So plus VB plus VE and plus VE plus VD. Okay, 0. That's all. So the loop is completed to write down the KVL equation. So put that equation in a put this coefficients in the matrix. So for row 3, that is with respect to L3, loop 3. So VB, for VA not there, so 0, VB plus 1, VC also not there, 0, VD plus 1, VE plus VE, so plus 1, VF not there, so 0. So that is how the tie-set matrix is created. Okay. So we need to know the tie-set. What is meant by tie-set? Okay. So that means loop, how many tie-sets are there? Basically, we need to know first point for a given tree. Okay. Or you have to take the tree. If tree is not given, you have to take the tree for the given graph. So for that, you have to know first thing, how many loops are there. That is the first point. Then second thing, you have to write down the KVL equations. Okay. Accordingly, using KVL, then put those equations in the matrix form by knowing the order of the tie-set matrix. Order of the tie-set matrix is given by loops. Okay, number of loops over number of branches. Okay, so by knowing that order, you can simply put those KVL equations, coefficients in the matrix. So that is how die-set matrix is formed. Next matrix. Next matrix is cut-set matrix. Next matrix is cut-set matrix. So you can see here, basically here also you need to know what is meant by cut-set. Okay, what is meant by a cut-set, what it consisting of. Then how to write down the equations to get the cut-set matrix. Okay, so basically cut-set means it is a minimal set of branches of the connected graph such that the removal of these branches causes the graph to be cut into exactly two parts. Such that the removal of these branches, cut set is a minimal number of branches. If we remove those branches, that original graph is divided into two parts. Okay, that's what they are telling. Now, a cut set consisting of what? A cut set consisting of one and only one branch of the tree together with the links. Okay, a cut set means it consisting of only one branch of the tree. Okay, together with the links. Only one branch of the tree, remaining are links. Okay, so that is a cut set. Now, what is how this cut set matrix is created? Next thing is how this cut set matrix is created. KCL is applied. Okay, see that the point is KCL is applicable to a cut set of a matrix. Okay, that means they are using KCL. For any lumped electrical network, the algebraic sum of all cut set branch currents is equal to 0. Algebraic sum of all cut set branch currents is 0. Now, while writing the KCL equation, okay, so we write the KCL equation for a cut set, for a considered cut set. Now, at the time of writing that KCL equation, okay, how to write down that? The point is assign positive sign. Assign positive sign for the current in a branch is direction coincide with the orientation of cut set. If that particular branch current direction is coincides with the orientation of the cut set. Okay, positive sign is taken if both are same, branch current direction and cut set direction, and vice versa. That means if they are opposite, consider the negative sign. See, let's see how to write the matrix. So here consider the circuit here shown. Okay, so 4 number of nodes and 6 branches. Okay, so it's equivalent graph. Already we know this. Okay, now the tree is taken. Write down. We look at the cut set matrix. How to write down this cut set matrix? Okay, for that we need a tree. Okay, we need a tree, and accordingly the remaining branches also represented with the dotted line. So here the tree taken is C, D, E with branches C, D, E, and remaining branches A, B, F are the links. Okay, so see that here first thing to how to get the cut set. Okay, we know that how to where to draw the cut set. So here cut sets are represented with the letter C, and the numbering is number of cut sets. So C1, C2, C3 and so on. Here see that you can see cut set, it is represented. So here we know basically cut set means what? It consisting of only one and only one branch of the tree together with the links. So cut set 1, this is a 1. So that means, see that I can draw, so you can understand. These are nodes, these are the branch, these are the, this is a tree, right? So this is F, A, B, D, E, E. So cut set. So this is a tree we have. So I can draw one cut set here. Yes or no? Because see that I say that cut set 1, C1, which consisting of only one branch of the tree and the remaining are the links. Yes or no? I have the only branch. What is a C is a only one branch of the tree and the remaining branches are the links. Yes or no? A and F are the links. That's why this becomes one cut set. Next, see that if you draw the cut set there, means if you cut the graph here to come, it will divide the total graph into two parts. Yes or no? If you cut here at this point where C1 is shown, okay, then what happens? The graph is divided into two parts. One side is only with node 1, the remaining side is node 2, 3, 4. So that is how a cut set mean. Now I can draw a cut set, okay, at node 2 also. Yes or no? Because this is 2. Because it has only one branch of the tree, that is D, and the remaining two are the links. A, B are the links. So that's why it is C2. Next, I can draw one more cut set at node 3. Okay? Yes or no? Where the branch is only one branch is E, remaining two are the links, B and F. Okay. So basically that is how cut sets for this tree. Okay. Now, to form the matrix, okay, what is that? We know that in the previous slide KCL is used. What is that says? If the cut set direction is same as a branch current direction, okay, then that will be plus. Okay, so that means we have to take the cut set direction. That is our choice. So for C1 direction I am taking like this. Okay, you can take other side also. Okay, that's why it is shown here. Come to this. So cut set C1 direction is taken like this. So C2 direction I am taking down. Okay, you can take up also. That's not a problem. That's also right. Okay, so that's why C2 direction is shown like this. Okay, next C3 direction is taken like this. So that is how cut set direction is assumed, and now apply KCL here. By KCL here, KCL equations for cut set 1. Okay, here basically before going into the equations, one more point. The order of the cut set matrix is given by number of cut sets over number of branches. Okay, number of cut sets over number of branches. So 3 cut sets we have. So the order of the matrix is cut set matrix 3 by 6. So that's why see, look here, cut sets. Okay, it is mentioned C1, C2, C3, branches A, B, C, D, E, F. Now, so, and the matrix is denoted with the letter capital C. Okay, now writing the KCL equations. So first KCL, first at cut set 1. C1 direction is shown. So what is first, okay. So cut set C1 direction is opposite to the VF direction. So that's why it is minus IF, and IA direction also opposite. So minus IA. IA direction is opposite to cut set direction. Yes or no? Cut set direction you can clearly see, right? Whatever is taken. So next IC is same as a cut set direction. So IC is plus. So that's how the equation is written. Now put the values in the matrix. IA is minus IA, so minus 1. B is 0, B is not there. So IC is plus IC, so plus 1. ID, IE also not there. So IF is minus IF, so minus 1. So first equation, first row. Next second cut set. Second cut set, okay, IA. IA direction, cut set C2 direction is taken down. So minus IA. Next plus ID, then minus IB equal to 0. That cut set is okay, touched with these three branches only. Okay, so now put that in equation. Minus IA, minus IB, IC not there, 0, ID plus ID, so 1, 0, 0. Now cut set 3. If you look at the cut set 3, so there plus IF, plus IF, minus IB, plus IA. So that's why you can come to the equation IA not there, minus IB, minus 1, IC not there, ID not there, zeros, IE is plus IE, IF is plus. So that is how the equations are written, and put that in an equation format, matrix format. So, excuse me. So that is how the cut set matrix is written. So if you have any questions, you can ask. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.